In this video, we will be talking about reverse mapping. Reverse mapping is a method we can use to attempt to predict the different types of gametes that would be produced by an individual that is heterozygous, as well as the probability or frequency of each of those gametes to occur. In this demonstration, we will be looking at a heterozygous individual that has a chromosome with 3 linked loci, each with 2 alleles. I will be using cats as an example. First step in reverse mapping is to look at a genetic map of the heterozygous cat. You can tell that the cat is heterozygous in the map since we have 2 different alleles in each of the 3 loci, yellow eyes at the top and blue eyes at the bottom. As you can see, the genetic map gives us the order of the 3 genes, where we have eye color on the left end, fur color in the middle, and hair length on the right end. The genetic map also gives us a map distance between the loci, where we have 15 centimorgans between eye color and fur color, and 20 centimorgans between fur color and hair length. A coefficient or coincidence value of 0.8 is also given. This data will help us determine the probability of each gamete to occur as we go along the reverse map. To only produce heterozygous progeny consistent with the genetic map, we need to illustrate a genetic cross. The heterozygous progeny, or our heterozygous cat, must have pure breeding parents that are both homozygous at all 3 loci and to have completely different phenotypes. Let's say the father has yellow eyes, black fur, and is short-haired, and the mother has blue eyes, orange fur, and is long-haired. The father's chromosome is represented by the Carolina panther pens, and the mother's chromosome is represented by the red pencils. Here you can see that both parents are homozygous on all 3 loci since they have the same alleles on each loci. When the pure breeding parents mate, they will both transfer a set of their alleles to their offspring. In this case, the father transfers its big Y, little f, and little h, and the mother transfers its little y, big F, and big H. This will produce a heterozygous cat with the father's genes at the top and the mother's genes at the bottom. Since the dominant trait is expressed over the recessive trait, the heterozygous cat will have yellow eyes, orange fur, and will be long-haired. Now that we know the genes that are present in the heterozygous cat, we can determine the gamete types that would be created by the heterozygous cat. We will be using a 3-point test cross between the heterozygous cat and a homozygous recessive cat. So here are all the gamete types that can be produced by the heterozygous cat and the events that occur. If we go back and look at our genetic map, we can label the events that would result in the gamete to be produced by each gamete type. We can determine these events by finding whether there are no crossovers, or NCO, single crossovers from the first to second loci, SCO1, single crossovers from the second to third loci, SCO2, or double crossovers, DCO. We now know the events that occur in each gamete type, so we can calculate the probabilities of all 8 of them. Here are the probabilities for each gamete type. The yellow-eyed, orange-furred, short-haired cat gamete, we know it is a DCO, so we first calculate the probability of DCO occurring by multiplying together the map distances and the coefficient value. So 0.15 times 0.2 times 0.8, and we get 0.024. We then take this number and multiply it by half to get the probability of the specific gamete. By doing this, we get 0.012. The yellow-eyed, orange-furred, long-haired cat gamete, we know it is an SCO1, so we subtract R1 to DCO. So 0.15 minus 0.024, and we get 0.126. We then take this number and multiply by half, so we get 0.063. This is the end of the presentation. Thank you for watching.